Thank you. Thank you, everyone, for joining today. My name is Matt Bandelt. I'm a faculty member at New Jersey Institute of Technology, and today what I'm going to talk about is the response of UHPC columns under moment rotation behavior. And part of this goes back to sort of developing some computational tools that help us understand behavior. And longer term, we're doing some experiments that really complement some of the work that Mohammed was showing maybe 30, 40 minutes ago. And what I'll do today is I'll talk about ultra-high performance concrete, but also other fiber reinforced materials that all sort of in common have these strain hardening characteristics that give us this unique mechanical behavior. And regardless of the actual tensile strength that we have, all of them in common have this ability to maintain tensile strength beyond initial crack formation. And what we know about UHPCs and these other types of materials is that they have enhanced mechanical performance, they improve damage tolerance, and they also have high durability. And the first two I'm highlighting because they specifically relate to structural response in their in moment rotation behavior for columns. And so, just an example, the main characteristic that was highlighted, I think by our very first presentation, was this ability to sort of limit the amount of spalling that occurs, especially under high compressive loads or lateral loads. And so this gives us a lot of benefits. One of the things that I've been interested in personally is the growth of UHPCs. We saw a slide about the economic growth of the materials, but if you look at a map of sort of on the FHWA's website of what's happened in the bridge sector, and you sort of plot the cumulative number of bridges that they've been recording over time, and what you see is this really nice exponential growth curve for UHPCs. And I've kind of been interested in what's sort of preventing us from using this in seismic design. We know that we have these excellent mechanical properties, and what are some of the obstacles or what are the things that we don't understand on the seismic space? And so some of the research questions that my group has been sort of looking at over the last few years are what gaps exist to characterize specifically system level behavior, because this is how we really quantify the benefits at a global response, how much better do our structural systems behave? And then in comparison to traditional concrete, what are the impacts both on, life safety as well as the economics of the whole situation as well? And there's been a lot of different research looking over the last 20 years or so for starting with sort of lower strength fiber reinforced concretes and now moving into UHPCs of these types of materials in different components within building systems for seismic related areas. So that's been everything from high deformation capacities in beams and columns to shear and bending deformations, improvements in reducing transverse reinforcement requirements, this idea of using them as structural fuses, et cetera. And in all cases, basically, we're looking at using these materials in locations where we expect damage, primarily in seismic design, and what are some of the potential benefits that we have. And so to sort of get you to understand why column behavior is so important, one of the things that we did recently was we looked at a design illustration of a 4-story frame subjected to seismic loading. And so this is a reinforced concrete frame that's been widely studied in the literature by Hazelton initially, and then it's been explored after that. And what we did is we replaced sort of all the beam end regions with HPFRCC materials. And you may be asking, well, why didn't you do columns? And as Mohammed mentioned before, there's very little column data for these types of systems. And so it makes it a lot harder to go and develop like a moment rotation response for a column, whereas for beams we have significantly more data. But we went and we did this for beams, and I could walk you through the whole process for that, but this is just a very high-level overview of this design illustration. And here's some of the responses that we had for these different types of systems. And the main thing I want to point out is we used a method called incremental dynamic analysis. And when we went through and engineered the system, we were able to reduce the probability of collapse under the maximum considered event by almost 40%. And so that has real impacts on life safety. It also has real impacts on, when we can get back into a building after an event, et cetera. And so it sort of highlights the very promising nature of UHPC and other fiber reinforced materials. But this was all done in light of sort of only having data on beam regions, right? So the lack of data on columns could potentially push this even further in terms of the types of performance that we might want to see. So more recently, we've been looking at a few different objectives. First, to identify some of the factors that influence the structural response of columns with these materials. And second, to develop tools to efficiently simulate their response. And so this is part of a longer project. The first year or so has just concluded, and we've been doing a lot of computational simulations to guide future experiments. And it's nice to see the community sort of working towards these experiments on a whole and learning a lot of information together. And so in this case, what we're doing is we're doing some computational simulations of future experiments that I'll talk about at the end of the presentation. And we're doing them both on UHPC and other fiber reinforced materials, all which have these strain hardening characteristics, UHPC being unique in the sense of the strength properties in particular. And we're looking at different reinforcement ratios, so modifying how much steel we have in sections, and then also the effects of axial load on these members as well. When we do these sorts of simulations, and we've validated them a lot on the beam side, so we know that they work very well in pure flexure. When we do the experiments later, we'll have a better sense of how they work under the combined effects of bending and axial load. But some of the things that we see here, so as we work our way from the black line to the dashed black line to the blue line, what we're looking at is the effects of increasing axial load. And one of the things that we see is that as you increase axial load, you actually increase not only the moment capacity, which makes sense just from a PM interaction diagram, but you increase the level at which, or the deformation that causes the failure on the tension side, in this case being the longitudinal reinforcement. And basically what's happening is as you apply that axial load, you're limiting the amount of strain that the rebar goes through, which allows the member to deform more. And then eventually it sort of pushes back and you get more on a compressive type of failure mode. It's worth noting that in the case of UHPCs, you're going to have much lower axial load ratios as compared to reinforced concrete because the strength of UHPC is so much higher. We're also looking at internally through our simulations what happens in terms of like the tensile reinforcement strain. So we're looking at here on the x-axis is tensile reinforcement strain just above and below the joint in our columns. And in this case, the blue simulation represents UHPC, and the green simulation represents a lower strength fiber reinforced concrete. And basically what happens is as you increase the tensile strength, you have these higher bond stresses, which this is nice, you literally just spoke about this 5 minutes ago, and you have these higher bond stresses, and what that does is it leads to more concentrated plastic strain distribution. So in our simulations, what we see is the effects of how bond influences sort of the next level, which is column response. We also looked at the combined effects basically of reinforcement ratio, the tensile strength of the material, and how axial load influences things. And what we're looking at on the x-axis is basically how much force does the rebar provide relative to the tensile strength of the material. On the y-axis, we're looking at the deformation at failure, and then these lines you see are different axial load ratios. And what we see is that drift capacity is a function of relative tensile strength. So basically, as you increase the relative tensile strength, you increase the drift capacity. And the other thing that we see, once again, across different materials is that initially sort of axial load lets you get to larger drifts, and then that pushes back down as you transition from a tensile failure state to something where you fail on the compressive side. And we've done this in addition to sort of what's going on in the reinforcement. We've also looked at computationally our plastic hinge length. So I'll just show you, from 0 to 20% axial load ratio, what happens in terms of damage, and you condense that damage by about 50% by increasing that axial load ratio, and you shift the failure modes. What we're working on now is using some of these models and then some physical experiments, which I'll show on the very last slide, to develop expressions for plastic hinge lengths so that we can go and simulate that building that I had before, but with UHPC columns. And so we're trying to do that. So once we have the plastic hinge lengths, then we can develop these concentrated plasticity models, which will allow us to do that. And so basically, the blue data is from some experiments that some experiments and simulations that we had done in my group. But those predictions of plastic hinge length were done without the column data that was needed. It was just done just on beams. And what we saw was that basically as you increase the axial load, what we developed for beams doesn't necessarily apply for plastic hinge length modeling of columns. And then the types of models that we use for reinforced concrete elements just generally don't work for UHPC because we have such a fundamentally different type of behavior. And so this is looking at some comparisons between experimental results and numerical simulations for maximum rotation capacity using some of these preliminary models that we've developed for plastic hinge length. And so they get us much closer than what we might use for traditional reinforced concrete. And again, sort of our next step is now to go back and basically rebuild those computational models that I had before of structural systems, but now put have columns in our models made with UHPC and other types of materials, which will then allow us to model the system level behavior and get a sense for, as I increase the amount of spectral acceleration on a structure, what does that influence the probability of collapse that I might have? And so some key kind of takeaways is that the drift capacity in columns is really a balance of both reinforcement properties and tensile strength. And at a big picture, what we're trying to do is systematically characterize the response of these columns to develop nonlinear time history analysis. In winter 2024, we're going to be doing some physical experiments looking at different axial load ratios on UHPC and other fiber reinforced concrete materials. And then those will be compared with the numerical examples that I had shown later, and we'll move on to that system level response. And so with that, I thank you, and I'd be happy to answer any questions that you have.